Welcome to the case study in insurance. In the next 15 minutes, I will present the approach and the main results of my final project. The goal of my project is to improve claims handling processes in the insurance industry. This is an important process in the industry that is highly manual today. Deep learning provides a lot of opportunities to improve this process. So what is the problem statement of my project? Main goal of my project is to classify images of cars having damages versus images of cars having no damages. I used Keras and TensorFlow with Python in my project, and the damage images have been scraped from Google Images, and images of all cars are augmented from the Stanford car dataset. I used the dataset prepared by a GitHub project that is referenced in the material. Here I have an overview of the technologies I used in my project. As starting point, I used Anaconda using the Jupyter Notebook. I used Python and my two main packages, NumPy and Matplotlib. I also used TensorFlow and Keras API for the implementation. So the dataset is about 146 megabyte large. It consists of 1,840 training, 460 validation images. 50% are damaged images or damaged cars. The other 50% are whole car images. The file format is in JPEG, and I downloaded the dataset from the referenced GitHub project of the car damage detective. Below you can see some screenshots of the images downloaded from the project. Here you have an overview of some of the images showing cars with damages and whole car images. As I said, the main goal of my project is to automatically classify these images to identify cars that have a damage. This is how the training data and the validation data looks like. So dataset contains 3 folders from data A1, data 2A, and data 3A. In my project, I only used the data 1A dataset. It has 2 subfolders for training and validation, and again, 2 subfolders for the damaged and the whole cars. The training validation split that is consistent in the data is 75% to 25%. Before starting with the modeling, I had to set up the environment and import some data into the system. Here you can see the links to my local file system referencing to the images in my project. I use libraries mainly from Keras, like the models, regularizers, and optimizers. I also use the image data generator, Matplotlib for the visualization, and NumPy. From the first iteration, I still had some overfitting in my model. Therefore, I decided to use data augmentation in the data preparation steps. First, all images are resized to 150 pixels. Since the training size is quite small, I decided to use these parameters for data augmentation. Below you have one selected image showing how the data augmentation is applied to the damaged car. Here you can see the code for the creation of the convolutional neural network. I used radar activation functions and an L2 regularizer in my model. In total, I have over 3 million trainable parameters. The code shows the image data generator that performs the data augmentation, and it shows how I train the model with the fit generator method. Here I used 30 epochs in my final iteration of the training. The slides shows some examples of successfully classified images. So you can see whole car images that are predicted as 1 and images of cars with a damage predicted as 0. This worked quite nicely, and the model is able to predict whether the car has a damage or not. You have an overview of the 3 iterations I performed in my project. I started with 15 epochs and no augmentation. As I said earlier, I saw some overfitting in this model after about 5 epochs, as you can see on the left-hand side. In the second iteration, I used data augmentation. As you can see here, the overfitting is reduced to some extent. Therefore, I decided to increase the number of epochs to 30 in my last iteration with data augmentation. Before I jump into the code samples, a quick summary of my results. So the results for training validation loss are already quite good, even though the dataset is quite small. Data augmentation improved the overall accuracy and reduced overfitting. In the predictions I performed, the classification of damages were identical to the actual values. So the classification worked pretty good. This is really interesting for the insurance industry because claims handling is a highly manual task and some aspects of the claim handling process could be automated with the model. For the future work, insurance enterprises have vast amount of data on existing claims, and this could be facilitated to improve the model in the future. Furthermore, future research could extend the model with more use cases. So one use case would be to identify the severity of the damage. So is the damage more or less severe? Maybe the estimation of the cost for the repair of the damage could be estimated. And I think it should also be possible to identify suitable repair shops for a particular kind of damage. Now, what were my lessons learned? I used the 75 to 25 ratio split in training and testing, and I think this worked quite good. I used data augmentation to reduce overfitting, and the model was quite quick on my local machine, so it was not necessary to run it on AWS or Azure. I think running even more epochs could improve the overall accuracy, since the data augmentation worked pretty good. Regarding the technology, Keras was quite comfortable. For the image classification task, it has a good development community. However, the data preparation and generation is a very laborious task. Now let's jump to the code and go through all the steps again. So in the beginning, I import the Keras library. And as I said earlier, the data is located in the local file system. Here you can see the paths to the train damage deer. And in the subsequent step, I print the number of images in this folder. Here we have 920 damage images for training and 920 whole images for training. So that we have in total 840 training images. Same for validation of damage and whole images. And here I started with the convolutional neural network with the model. I used value activation functions and started with a regularizer. In total, I have 3 million trainable parameters. And I also used cross entropy as loss function. Here you can see how I trimmed and rescaled the images to the same size. And I used the image data generator to feed the model. This is the first iteration of the training for the model. As I said earlier, I used 15 epochs for the first iteration and applied no data augmentation. On average, one epoch took a little bit more than 2 minutes, so this was quite fast. I used the history returned by the model fit function to print the overall training validation accuracy and the training and validation loss. As you can see, after about 5 epochs, we have some overfitting here. Therefore, I decided in the next step to use some data augmentation with the image data generator. Similar to the exercise, I used the skeleton to take a random picture and print how the data augmentation manipulates the picture. Here you can see some rotations and flippings of the picture. Now, after the data augmentation, I started again with the same model, with the same hyperparameters. Here I start fitting the model, again with 15 epochs. Now, looking at the training validation accuracy and training validation loss, you can see that the overfitting has somewhat improved. At this point, I started to play around a little bit and predict damaged images. So as you can see here, I load the first iteration of the model. I select one image from the damage folder, and I use predict classes to classify this image. Executing this code takes the image, plots the image, and returns 0 as the correct damage class. Here I have an example of a wall car. Again, executing this, prints predicted one as the correct class. I repeated the step several times, and as you can see, the model predicted the correct class. For the next step, I repeated the training with the same model and the same parameters, except for the number of epochs. I increased the number of epochs to 30, and the data augmentation improved the overfitting. And as you can see from the overall training and validation accuracy, training and validation loss, the overall accuracy improved, and the model performs quite good. For future work, as I said, one could extend the use case by predicting severity of a damage, indicating whether it's a small damage or a large damage. Another use case could be to identify suitable repair shops for the kind of damage of the given car. And finally, one possibility would be to predict costs of the damage or repair costs for the insurance enterprise.